Hey, good morning, everybody. This is Mr. Ainsworth, and we're going to get into your 7A2 activity here in MRWC. And before we even get into this here, I assume that everybody went through my prep discussion prior to this activity. Don't even attempt this activity unless you've gone through that discussion. So in this discussion that I have at the top of the screen here, I talked about 6 different families of functions. And the first one was linear functions. We found out that they have no restrictions and their domain is a set of all reals. Okay, we looked at the graph, we analyzed all of these functions, and we did it analytically, and we also did it graphically using Desmos. In the second one, we looked at this quadratic function, and it was another polynomial function, just like number 1, but it's second degree, not first degree. It also has no restrictions, and it had a domain in this set of all reals, and all quadratic functions have that domain. All linear functions have that same domain as set of all reals. Number 3, we found out that rational functions like this one, rational or fractional functions, because you cannot divide by 0, have restrictions, and all rational functions have restrictions. And then number 4, we talked about the exponential function family here. This one's base 2. This had an unrestricted domain as well, so it had a set of all reals for the domain. And then we took a look at number 5 here, which is the root function. So it's the square root function family here. And because you cannot square root a negative and be real, this function has restrictions too. All square root functions have restrictions. So it's all reals either less than or greater than some value. So we took x plus 4, set it greater than or equal to 0, because you can't square root a negative. And we found out the domain was all reals greater than or equal to negative 4. And then the last family of functions that we talked about was the natural log function. And the argument here, this x plus 4 is called the argument. That's got to be greater than 0. So we solved that simple inequality and found out that this domain was all reals greater than negative 4. And we looked at that as a graph too. So make sure you go through this prep here. Make sure you watch that before you get into this activity, because it's a little bit more involved than you think. Desmos is required here. Notice that I have all the functions already inputted in Desmos. You need to create an account, and you can enter the functions in, save it, make sure you name it at the very top with the appropriate name, like 7A2 activity, and you save all your work as you go. Okay, so we need to do a few things in this activity right here. We need to find the domain of each function algebraically. Okay, so that's the first thing. Number 1. Number 2, we need to express it in interval notation. That's the second thing. And then third, right here, we need to use a graphing tool like Desmos. Okay, it doesn't have to be Desmos. It can be GeoGebra. You can use a TID4. You can use any graphing tool that you want, and use that to confirm the correct domain. Okay, so first of all, we have f of p here. So we have f of p is equal to 3p minus 2 divided by 5. And this is a first degree function, so it's linear. So that's the first thing that I notice. Okay, it's a linear function. So I already know the domain, because all linear functions have a domain which is the set of all reals. Now when you enter this in Desmos, notice that we're dealing with the f of p here, and in Desmos you do f of x or y in terms of x. So the same function, just so you know, is f of x, so I'm just switching variables here from p to x, is equal to 3x minus 2 all divided by 5. You need to know how to rewrite the functions in terms of x, because when you go to Desmos, like at the very top one here, look at this first one here, you'll notice that it's a line, it's a linear function. Okay, this is the same as 3/5 x minus 2/5. Okay, so if you divide both terms up top by 5, you get a linear function. And because of that, the domain is a set of reals. So the domain, I'm going to write down words, all reals. Okay, in symbols, it's from negative infinity to infinity. That's interval notation. That's why you say all reals. That's how you say it. X can be any real number. All right, from negative infinity to positive infinity. And that's the case for all linear functions. Okay, so remember that. If you do, there's no work needed. You don't even need to look at the graph. Although we're seeing the graph right here, notice that it's a line with no holes, asymptotes, breaks in the function, no discontinuities. Okay, x can be negative, x can be 0, x can be positive. And so that means that x can be any real number. Now, not the case for the rational function here. In this next function here, I'm going to write it in terms of x instead of p. So I have 5 divided by 3x minus 2. Now, rational functions have restrictions. Okay, this is called a rational function. And all rational functions have restrictions. And you need to focus in on the domain, because rational functions, you have to remember one basic thing, and I talked about it in my prep lesson here, like on number 3. You cannot divide by 0, man. Okay, because of that, you got to restrict the domain. Okay, so when you look at this, you have to solve a simple equation to analyze the domain. You got to figure out when, for what value of x makes 3x minus 2 equal to 0. Okay, because 3x, 3x minus 2, okay, that cannot be equal to 0. Because if it's 0, guys, you would have 5 divided by 0, and 5 divided by 0 is undefined. So whatever x is here, we got to solve this. You got to restrict that from the domain. It's going to be all reals except this. So you add 2, do some simple math, you get 3x equals 2, or not equal to 2, divide by 3, and okay, right here, x cannot be equal to 2/3. So the domain is all reals except 2/3. And you have to write that in interval notation. Okay, so running out of room here. So I'll tell you what, I'll do it over here in the margin. Okay, so if it's all reals except 2/3, okay, let me draw a little graph here. So if this is 2/3, okay, x can be, it can't be 2/3, so it's got to be open here, and it could be to the left of it towards negative infinity, and it could be to the right of it towards positive infinity. So you have to write this domain as 2 intervals. The first interval on the left is from negative infinity to 2/3, union, okay, from 2/3 to infinity. Okay, and that's the domain for the second function. Okay, I just can't fit it all in here. That's why, you know, some of these activities, guys, yeah, you need some graph paper and do some work on the side. It's kind of hard to fit it in these little spaces, especially if you're going to show your thinking, like I'm doing. Okay, because I'm actually explaining, and when I explain, I just do it. Okay, if I was doing this by myself, I would just write the answer because I just know it. But I'm explaining here, so obviously I have to show my thinking. Okay, number 3 is a root function. Now, a root function is just like number 5, and I said that all square root functions are only defined when the radicand is positive or 0, greater than or equal to 0. And so all square root functions have to be restricted. Okay, so here we go. 2 minus w here, the square root of 2 minus w. The radicand, the term underneath the radical is called the radicand. This 2 minus w has to be greater than or equal to 0. Okay, greater than or equal to 0. Because you can't square root a negative. I mean, use your basic common sense here. So, in doing this, oh, I forgot to show the second function. That's okay. I'll go back to Desmos here in a minute. You need to solve the inequality 2 minus w. I'll tell you what, I'll do it in the margin here. I'll do it down here. 2 minus w, so 2 minus w is got to be greater than or equal to 0. Well, let's just isolate w. So I'm going to add w. I get 2 is greater than or equal to w. And if 2 is greater than or equal to w, then w is less than or equal to 2. Okay? So the domain here is all reals less than or equal to 2. So the domain, D, is all reals less than or equal to 2. So from negative infinity to 2 inclusively. So closed on the right side, open on the left. Okay? All reals less than or equal to 2. Now why is that? So let's enter it in. So look at, I'm going to turn off the first function here. Now y equals the square root of 2 minus x is the same function as this. So I switched from s to y, and I switched from w to x, so I can use Desmos. So let's go ahead and take a look at this here. I'm going to just take a look on this graph here. Notice, okay, it's black. Notice that the starting point right here is at 2, 0, where x is 2. Look at, you're on 2 on the x-axis. and it doesn't go to the right, it goes to the left. So the values of x that are on this function, if you just pick a point and just grab a point on the graph, and on Desmos you can just trace the graph. Notice that we can go to the left and go towards negative infinity. And the farther you go left, the more negative the x value becomes. Y is positive, but x is negative. And so that's why this function only exists to the left of 2. And that's why the domain here is from negative infinity to positive 2 inclusively. So closed on the right. So you can see that from the graph, and you can see that from the function. Okay, next one here. So 5m minus 2k equals 0, where k is a function of m. So let's solve for k. So let's just subtract 5m. And I get 2k is equal to negative 5m. Divide by 2. I get k is equal to negative 5 halves m. And that's another linear function. This is linear. This is the same thing, you guys, as y is equal to negative 5 halves x. It's linear. Okay, it's a linear function. And because of that, the domain, okay, where m is the domain here, is a set of all reals. So from negative infinity to positive infinity as an interval. The set of all reals. Remember, all linear functions have a domain that is the set of all reals. And I graphed it here, so I'm going to go to Desmos here, turn on number 5, turn off number 4. And you can see, look at this. It's just a line with a negative slope. Down 5, right 2. Okay, down 5, right 2. Down 5, right 2. Down 5, right 2. You get, simple. When you see a line, a linear function, the domain is always the set of all reals. You should write that down somewhere. Okay, linear functions. Okay, the domain, all reals. Every single time. I've said it so many times, but you guys got to remember it. Okay, next one. Next one, w of u equals 1 minus u. Okay, this is the same thing as y is equal to 1 minus x. Okay, so when you enter this in Desmos, that's all you do. And then where I switch from u to x, so x is greater than 1. So x is greater than 1. And so this right here is the domain. It's been restricted. So the domain is from 1 to infinity. So they actually gave us the domain on this function. Now if you want to see what it looks like, you just go to your graph and you type it in. But one thing you have to learn on Desmos here is how to write in the restricted domains. And whenever you put a restricted domain in, use these curly brackets. Okay, they're on the keyboard and they're right next to the square brackets, right next to the letter P. Okay, but you have to use this shift button to get these brackets. And so this is the restriction on the domain. It's from 1 to infinity, and that's why this graph starts at 1. Look at that. It starts at 1 and goes to the right, because it only exists to the right of 1, because the domain has been restricted, as I keep on saying. Okay, h. Now h is, you take 3x plus 2 and multiply by x minus 1. And if you notice that if you multiply using FOIL, 3x times x, you get 3x squared. So this is a quadratic function right here. This is the same type of function as we talked about in, it's not up here. Well, it's a quadratic function, kind of like number 2 actually, because that's a second degree function too. And as we talked about earlier, there's no restrictions for quadratic functions of this type. Okay, y in terms of x squared here. And so the domain is going to be the set of reals, and I'll show you that on the graph here in a minute. So this is a quadratic function, because again, 3x times x is 3x squared. It's x squared, guys. It's a second degree quadratic function. Second degree called quadratic function. And all second degree quadratic functions, the domain is the set of all reals. You can substitute anything you want in that quadratic function and get a real number back. So when you write the set of all reals, you just say negative infinity to infinity as an interval. And that's just a nice concise way of saying, hey, x can be any real number from negative infinity to positive infinity. And that's the case for all second degree quadratic functions of this form. Okay, not so with the rational function here. Now, as I said earlier in our previous discussion, in number 3, all rational functions have restricted domains because you can't divide by 0, like I talked about in the second one. So when you handle this right here, you have to figure out when or where or what points makes the denominator 0 and restrict that out of the domain. Okay, so when is 3x plus 2 equal to 0? So let's find that out. Let's do a little homework here. So I'm going to look at the denominator here, denominator. So when I got to take 3x plus 2, it can't be equal to 0 because 0 times anything is 0, and 1 divided by 0 is undefined. So whatever this is, it can't be equal to 0. So just solve for x and you get 3x, whatever that is, it can't be equal to negative 2, divide by 3. So x cannot be equal to negative 2/3. Also, you got another binomial here in the denominator. This x minus 1, that can't be equal to 0 either. So you simply add 1, simple. X cannot be equal to 1. So when you do this on the number line, if you want to, because you have to write the domain in terms of intervals. Negative 2/3 is here, okay, and then 1's over here somewhere, just sketch. And if it can't be equal to negative 2/3 and it can't be equal to 1, go open there. It could be any number to the left towards negative infinity, any number in between, and then so, or to the left, or in between, or to the right towards positive infinity. We talked about this in our previous activity in 7A1. We had a one just like this, if you recall. And so this right here, this interval is from negative infinity to negative 2/3 open, union. The one in the middle is from negative 2/3 to 1, so negative 2/3 to 1, and then union. And then the one to the right is 1 to infinity, so 1 comma infinity. And this is the domain, written in interval notation for this. The other way you can say that using inequalities is you just say x is not equal to negative 2/3 comma 1. So sometimes using inequalities, it's a lot easier to write. This right here, this inequality notation, all reals not equal to negative 2/3 and 1, is the same as interval notation, and it just gives you an example that, hey, sometimes it's easier to use inequalities versus interval notation, and vice versa. So it all depends on, the function and what you're doing. Okay, let's get back to the next one here. This is another rational function, and if you just look at the denominator here, x minus 1, that can't be equal to 0, which tells you that x can't be 1, because 1 minus 1 is 0, and you can't divide by 0, man. No way, you never have been. All right, so this tells you that x can't be equal to 1, and that's the domain. So to describe this, if you want to graph this, so here's 1, let's say. So it's open at 1, and you can go left to negative infinity, go right to positive infinity. So if you're going to describe the domain using intervals, you'd say, okay, negative infinity, whoops, not 8, negative infinity to 1, that's on the left side, union, on the right side, 1 to infinity. So this is the domain using interval notation for J. Okay? Okay. Now, a couple more here. We got the log of x plus 1. Now, as I told you before in the previous lesson, okay, the argument has got to be positive only. Okay, I don't care whether it's a natural log or any kind of log here. The argument has to be positive. It can never be 0 or negative. So all you do is say, okay, the argument here is x plus 1. That's where you focus your attention. And that's got to be greater than 1. So let me write that down. Greater than 0. So you got to think, okay, so for what values of x plus 1 give you greater than 0? Well, if you solve this, x has to be greater than negative 1. And that's the domain. All right, so the domain here, just bring it down here so I have some more room, okay, is from negative 1 to infinity. That's the domain for g of x up here. Okay, all reals greater than negative 1. So open at negative 1 to positive infinity. Now the last one here, this is a constant. You guys saw e, this is the base of the natural log. It's a constant function. Oh, you know what? Let me back up here. Let me go to the log question. Do I have it up here? No, I don't. Actually, why I don't have that? Let me add a function in here. So let me type in log of x plus 1. So go functions, miscellaneous, type in log, okay, and then type in x plus 1. That's how simple it is to use in Desmos. Piece of cake. Well, let me put y equals this. Okay, so y equals, there's your function. So this is g of x right here. Let me turn off the previous one, and so you can just look at one function at a time. And look at this, the function, it looks like it's asymptotic here to x equals 1, and it only exists, okay, so look at that, at -1 it's undefined. As I told you, -1 plus 1 is 0, and the log of 0 is undefined. It only exists to the right. So x cannot be -1, it only could be to the right of -1, so -1 to infinity. So that just verifies what I just said right here in terms of the domain. Now, let's turn that off and let's type in y equals e. Okay, f of x equals e is the same thing as y equals e. That's a horizontal line, look at this. So e, just so you know, e is that famous Euler constant, 2.718. Notice it tells you right here, 2.718. And notice it's up here, it's a horizontal line right between 2 and 3. It's a little less than 3. 2.7 is a little bit less than 3. And notice that a horizontal line, it's defined everywhere. And because it's a constant function here, it doesn't matter what x is, because x is not even involved, so x can be anything. So in this one here, the domain is a set of all reals. And that's the case for all constant functions. This is called a constant function because e is a constant. It never changes. It's always 2.718, 2818, and so on. Okay, so the domain is a set of all reals. Okay, we're rocking. Okay, so that's the first part of the activity. Let's go to the second part. Okay, this is pretty involved here too. So again, this is 7a2. So we need to do a few things. How do the graphs compare? So we need to graph them in Desmos and sketch them here. Use a graphing tool like Desmos to confirm. What do you notice? What are your conclusions about the pair of functions? How are they similar? How are they different? And then what is the domain and what is the range for each function? So we have some work to do. Okay, so you guys do your sketching. You sketch the graphs here. And I'm just going to import them and do some screen clipping because I'm all digital. Okay, so you guys do your sketches. All right, you sketch the graphs. So let's look at these one at a time. So let's turn on the first function here. The first function is y equals the square root of x squared. And this is what it looks like right here. So let me grab this. And again, so you type your functions in, and then you sketch it on your papers. Okay, I'm just going to clip my graphs in so we can discuss them. Now the next graph is y equals x. So I'm going to turn off the first one, keep on the second one, and notice it's just a line. Y equals x is a linear function. So it's a very simple function. It's just a simple linear function. Okay? All right. And then when you put them side by side, so just sketch them on your paper here. I'm importing them in. These are from Desmos here. You can easily see what the domain and the range are for each of these. So let's talk about that, because it asks you to determine the domain and the range. Okay, so for the first one here, x can be any real number here. You can square 0 and then square root it, no problem. You can square a negative, no problem, and then square root a positive. X can be positive as well. Okay, so here on the left side, the domain is a set of all reals. Okay, all reals. From negative infinity to positive infinity. The range is not. Okay, all the y values here are above the x-axis. Y can be negative, or excuse me, 0 at the vertex. It can be positive up here on the left. And it can be positive on the right. So the y values are obviously greater than or equal to 0, and the way you say that is you go not open, you say closed at 0 to positive infinity, because it keeps on going up, right? It could be 0 on up, all right, to positive infinity. Now on the right side, these functions are similar because the square root of x looks like it's x, right? But even though the square root of x squared equals x, the graphs of the functions are different. See, here we have a line and here we don't. Okay, so here on the right side, the domain is a set of all reals. Okay, from negative infinity to positive infinity. The range, same thing. Y can be negative down below here, it could be 0 at the origin, or it could be positive. So the range is all reals, from negative infinity to positive infinity. So the functions look similar. I mean, the square root of x squared is x. However, because you're squaring first on f of x, you got to square it first and then square root. This function will always be positive because whatever you square, whether it's negative or positive, it doesn't matter, will be a positive number, and the square root of a positive number will give you a positive number. And that's why it goes up, and it never goes below the axis. And that's why they are similar, but actually different looking in respect to the graphs. Okay, now let's go to the next one here. How do these look similar, okay? The square root of x squared versus the square root of x, then squared. You got to follow the order of operations here. So go to decimals, enter the functions in, and turn them on, okay? So here's the first function. Well, we got to change the color there. How do I change the color here? I gotta learn how to do that. Anyways, okay, so let's just look at them one at a time. So on the screen, you're looking at, we already have that function here, so we already did this one. So let me just grab this function here. It's the same as the one over here. So let me just bring it over. There we go. Okay, but we need the new function here. So I'm going to turn this one off, and I'm going to graph the second one. And notice the second one's different. It's just it's the right side only. Holy cow, it only exists to the right of 0. All right, so this one's different, obviously. Let me just put them side by side. Okay, and again, you just sketch these graphs on your paper because they are different. So, and because they're, uh-oh, what happened here? Come on. There we go. Because they are different, you're going to have to obviously analyze them and figure out what the differences are and why are they different. Okay, why are they similar? Why are they different? So we know the domain here on the first graph, f of x. That's the first one here. So the domain is a set of all reals from negative infinity to infinity. The range, we already talked about it in the first one here. Since it opens up, so the y values are positive or 0. So from 0 to infinity. So from 0 to infinity. Over on the right, different story. The smallest x value is 0. So it's from 0 to infinity. Again, this is positive infinity over here to the right as you go towards the right. And then positive infinity going up as well. So the y values, the lowest value you can have is 0, and it goes on up. So the range is from 0 to infinity as well. And notice these are slightly different. The domains are different here. The one on the right has a restricted domain. And the reason why is because in the g of x here, you have to square root x first and then square it. As opposed to the first step function here, you square first and then square root. So in the second function, knowing that you square root first, you can't square root a negative. Alright, so the x there, it has to be greater than 0. Positive only. Okay, or actually is greater than or equal to 0. So 0 or positive. 0 or positive. Because you guys can't square a negative. You get a complex number there. And we can only graph real numbers on the real coordinate plane. Okay, it's as simple as that. Okay, next one. So let's turn the previous function off. Let's put in the first one here. And look at this. It's a line. Well, we think it's a line. Okay, but if you cruise along the line, what happens? What happens at x equals 2? Because we got a problem at 2, because 2 minus 2 is 0. And you, as I said before, you can't divide by 0. So what happens at 2? Oh, look what happened. I mean, just look at the calculator, look at Desmos. When I substitute in 2, it says undefined. See? Undefined. And so it actually has a hole there, right there at 2 comma 4, there's a hole in the graph. Let's see if I can make that happen. So at 2 comma 0, yeah, oh cool, I just made it happen. There's actually a hole in the graph. So when you sketch this thing, make sure you sketch it properly with a hole. Look at that. That's pretty cool. I love this technology. Okay, so there's a hole at 2 comma 4. So let me highlight that. So x cannot be hang on for a second. Okay, so we have a hole at x equals 2. So x cannot be equal to 2. That's the domain. Okay, all reals not equal to 2. And you can see that the hole, there is at 2 comma 4. Okay, the function is not defined at 2 because 2 minus 2 is 0, and you can't divide by 0. So the range, a little bit different. The hole is at 2 comma 4, so y can't be 4 because there's a hole there. So the range is all reals not equal to 4. In interval notation, you can say negative infinity to 4, union 4 to infinity as an interval if you like. Okay. Now the other function, I'm going to turn this one off and turn the other one on. It's just a line. Okay, it's a linear function, and as you guys know, the domain is a set of all reals. So this one's just a simple line, and watch this. When I put them side by side, you'll notice that they look similar, right? They look very similar. They're the same line, in fact, but this line doesn't have a hole. So on the one on the right, there's no hole. Okay, it's a line, and the domain, well, it's the same. It's all reals, as you know. It's a linear function, and linear functions have the same domain all the time. The range is also the set of reals. Okay, and it's unrestricted because there's no hole in a linear function. There's no place where it's undefined. In rational functions, there's always a place where it's undefined. Okay, if the variable's in the denominator. So keep that in mind. So they are similar but different because the one on the left has a restricted domain, it has a hole in it, and the one on the right, well, it's unrestricted, and so the domain and range is a set of all reals. Okay, now these guys right here, log functions. So let's enter it in Desmos. So it's this crazy looking function right here. Okay, and it looks like it has a vertical asymptote, which is the y-axis here. It's asymptotic there. So if you go down low towards negative infinity, it's asymptotic there. On the right side, it's also asymptotic as you go down towards negative infinity. All right. So x can be it can be negative on the left, it could be positive on the right, but it can't be 0. As I said, this right here can never be 0. It's got to be positive only. Okay, greater than 0. So x cannot be equal to 0, or it's got to be greater than 0. Actually, in this case, it's x squared. So when you square a negative, you get a positive. So this is always positive. So x can be negative, it can be positive, but it cannot be equal to 0. There's your domain. So as an interval, well, I'll talk about that in a minute. Let me get the graph here first. Let me bring in the graph. I forgot to do that. Okay, here's the graph. Let's get the other function here too. So notice it's only the right half, not the full function. So these are different. They look similar, the same curves actually, but the second function is only on the right side of it. Okay, so keep that in mind. So there's g of x. Okay, so it's the same curve, okay, but these are different functions. Because if you square the number first, then take the log, following the order of operations, that gives you a different result than if you take the log of x first and then multiply by 2. Okay, so they're different. So the domain here on this one is all reals not equal to 0. Okay, so you write an interval notation, so you say negative infinity to 0, union 0 to infinity. The range, you can go as high as you want or low as you want. So it's a set of reals. It could be any real number. And on this one here, the domain is strictly positive. So x is strictly greater than 0. because, well, this is positive only. As I said in my previous videos, it's positive only. Okay, and I talked about the reasons why earlier, and I'm not going to get into it now, but there's a reason for that. But just remember that. Positive only, x has to be greater than 0. So as an interval, you just say 0 into infinity. In the range, same as the previous one, y can be negative, y can be 0, y can be positive. So all reals. So from negative infinity to positive infinity. All right, that, my friends, was a lot. These activities, they seem simple, but they're not, okay? They are not simple, and there's a lot of conceptual development involved in these activities. So you really have to watch the prep videos that I make, because these are more detailed than you think, more abstract than you think. And so make sure you go through my prep videos first that I put in Canvas, like on this previous discussion here. Otherwise, God help you, you're going to be trying to figure this out on your own. So very, very detailed. So do your best. It's a video, so you can rewind it and listen to any portion of it again. But strive for understanding, full understanding. Okay, so go slow through the videos, pause, play, rewind as you move through the videos, and listen to it as much as you want. But this is your goal. This is what your activities should look like when you submit them into Canvas to get full credit. They need to be detailed and show your thinking. Okay, you can't just put down a result. Okay. All right, and then of course you got to submit your Desmos work. So when you do that, you hit the share button. You do not submit, okay, this link. You print to a PDF and you do a paperless. All right, so you go to your print dialog, you select as a PDF, and you save it to your folder on your desktop, all this work, and then you open it up and you can submit the PDF to Canvas. So you never need to print. You save your ink, save your paper, print it as a PDF, okay, and go paperless. Okay, and that, my friends, is how you do that. So you got your Desmos work here, you got all your graphs. Make sure you save it so that at the end of the section, when we start getting ready for an exam, you have all your functions in there and you can use them as a good review and a good resource to get ready for your exam. All right, this is Mr. Ainsworth. That's all I got for you right now. I'll see you in my next activity. Bye-bye.